In this tutorial, we're going to calculate the impulse and corresponding change in velocity of an object subject to a time-dependent force. So imagine that we're given a force of this form applied to an object between t equals 0 and t equals 6.5 seconds. We're also told that the object's mass is 19 kilograms. Well, to calculate the impulse, we'll be taking the time integral of f dt. Ultimately, if we want to relate that to a change in velocity, we'll use the relation that the impulse is the change in momentum, and that momentum is m times v. If we graph out this force as a function of time for the specified time range, the curve looks something like this, and because the impulse is the integral of f dt, the impulse would correspond to the area between this curve and f equals 0. I've color-coded this because the part above f equals 0, the blue part, contributes positively to the impulse, whereas the section below f equals 0, namely the red part, contributes negatively. So all we can really figure out graphically is that the overall impulse should be positive. The area of the blue part is bigger than the area of the red part after all, but otherwise it's very challenging to just guess the magnitude of the impulse by looking at this curve. We really have to integrate. So let's do that now. So we clear this out, and we'll just start with j equals the integral of f dt, where I've put in the limits of integration from our time range 0 to 6.5 seconds. Now we'll substitute in the form of the force, and we can pull out the constants, 15 newtons times I hat, remember I hat is a constant, and now we're left with the integral of sine quantity 2 pi t over 8 seconds dt. To solve this integral, let's do a substitution. I'm going to define a new variable mu, which is just equal to the argument of the sine function, namely 2 pi t over 8.0 seconds. If that's true, then d mu must be 2 pi divided by 8.0 seconds times dt. So we can substitute these two expressions into our expression for j to simplify the integral, like so, where I want to call your attention to the fact that I changed the limits of integration, at least the upper limit here, by using the expression mu applied to 6.5 seconds for t. I also technically did that to the lower limit of integration, but 2 pi times 0 divided by 8 is still 0. Also, this part of the integral, 8.0 seconds divided by 2 pi times d mu, just comes from rearranging this expression, solving for dt, and plugging it back into our previous expression for j. So now let's simplify our new expression for j. We can pull out the constant 8 seconds divided by 2 pi, and we'll simplify that upper limit of integration a little bit, and now we just have the integral of sine mu d mu. Well, that's an easy one. The integral of sine is negative cosine, so if I combine those two constants out front to be 19.099 newtons times seconds I hat, the integral just becomes negative cosine evaluated between 0 and 5.105, so we can evaluate that, simplify things a little bit, and we get that the impulse is equal to 11.8 newtons times seconds times I hat. It still retains the direction vector. After all, both impulse and force are vectors. The usual reasons to calculate the impulse are either that we want to know the change in momentum or the change in velocity of an object, so let's keep that up there and use the relation that the impulse j equals the change in momentum delta p. Well, we're interested in the change in velocity. Fortunately, our object has a constant mass, 19 kilograms, so we can rewrite delta p as m times delta v. Well, now it's simple to solve for the change in velocity. Delta v is just going to be j divided by m, and we have both of those values. We'll plug in j equals 11.79 newtons times seconds I hat, using a little more precision than our final answer, and we'll divide by 19 kilograms, the mass, to get that the change in velocity must be 0.62 meters per second in the positive x direction, or times I hat if you like. Now we don't actually know the final velocity of the object, we only know the change in its velocity. You would need to know the initial velocity to compute the final velocity at t equals 6.5 seconds.